So share the screen for you. Right. So if you remember last week, last Monday, I have discussed one simple example, which is about a free particle. And I assume that you can do this example, the rest of the things in this example, you should be able to do it yourself, right? So it's basically a free particle that you can directly write the kinetic energy, and then I showed you how to convert the Cartesian coordinates into polar coordinates, and then write the same equations. And this is very similar to converting Cartesian coordinates into generalized coordinates, right? In this particular example, so if I just remind it, so there was a particle on the free space with coordinates x and y. So I assume that this will, initially this will have, so let me just go to that. So there is a particle. Initially, if there is a particle, if you want to fix the particle on the space, you need three coordinates, right? X, Y, and Z. So this is what we normally called as degrees of freedom, right? So there will be 3 degrees of freedom. But if I assume that the particle is constrained to move on a surface, then there will be only two coordinates, right? Because you have this constraint which it can only move on a surface. Think this as a surface, and the particle only moves on this surface. So which means it will move either to the x direction or towards the y direction, right? The z will be zero. Or the c direction, there will be no motion to the c direction, so that you apply the constraint and then you reduce the number of degrees of freedom from 3 to 2, right? So that's how you understand it. Now you have 2 degrees of freedom, and since this is a free particle, for the when you are going to apply the Lagrange equation, all you need to do is write the kinetic energy of this particle. Now, if this is in Cartesian coordinates, the kinetic energy will be x dot squared plus y dot squared. Right? So it will be very simple. And then the potential energy, we discussed that it will be zero for the free particle. Right? Now there are two coordinates, 2 degrees of freedom. And can anyone tell me that how many Lagrange equations that I should have for this system? 1, 2, 3, 4. How many Lagrange equations that I should have in this for this system? Okay, so I have one answer. How about the others? Two answers. Right. So I got a lot of messages for the chat here telling that it will be 2 degrees of freedom, which is correct because initially we had 3 degrees of freedom, but applying the constraint, you reduce the number of degrees of freedom to 2. So 2 degrees of freedom means you have two coordinates, which means basically two generalized coordinates, and the number of degrees of freedom that you have in the system should be equal to number of Lagrange equations that you have to write, right, for that particular system. So that's how it works. And so this is t equal half mx dot squared plus y dot squared. So if the Lagrange equation that we had was, remember, daba over daba t, daba L over daba q dot minus daba L over daba q. So this is how you write the Lagrange equation, and L here is kinetic energy minus potential energy, and the kinetic energy is half m x dot squared plus y dot squared, and minus potential energy is 0. So it's the Lagrangian is just the kinetic energy, right? Now this q right here is it represents the generalized coordinates. Now at this particular situation, generalized coordinates are just Cartesian coordinates because this is a very simple problem. So there are two generalized coordinates. One is x dot and the other one is y dot. So which means there will be two Lagrange equations. One will be, so q dot will be replaced from x dot and x. So this will be one Lagrange equation, and if you substitute daba L over daba x dot from this equation right here, will be just mx dot, and when you take the time derivative of that, the answer for this section will be mx double dot minus the next one is daba L over daba x, and you can see that there are no x terms in the Lagrangian, so the daba L over daba x will be 0, right? Minus 0. So basically the answer will be mx dot equals 0, right? So there are no external forces. This is like F equal ma now, right? So you can get the same answer by applying the Newton's law as well, right? So how about the answer for the other Lagrange equation? Daba L over daba y dot minus daba L over daba y equal to 0. Will it be the same? Will it be different? For this, the second Lagrange equation, it will be the same answer, right? Basically, the expression is symmetrical, and what you would have is my dot double dot equals 0 if you solve this equation. Right? So I'm not going to solve it. I mean, it's a very simple equation. And this is one way of solving this equation. And if you want, you can write the, if you want, you can convert this into polar coordinates. And then your coordinate system will have two coordinates. One will be r and the other one will be theta, right? So you can write the expressions in terms of Cartesian coordinates, and then you can convert it into, I mean, if you want, you can take the generalized coordinates as Cartesian coordinates in this particular situation. But at the same time, you can actually think about converting the expression into Cartesian coordinates, sorry, polar coordinates, and use that expression to write the Lagrange equation, which will be the same equations but is written in a slightly different way. One way of doing this, actually, I guess we discussed about this last time, right? So I'm not going to go through it. And if you remember that I wrote this kinetic energy as half m r dot square plus r square theta dot square. Right? So this is what you get when you convert x and y's into polar coordinates and write the kinetic energy. Now you can, for this equation, your coordinates are r and theta. So if you need to write the Lagrange equation, then what you need to do is write it in terms of minus dava L over dava R equals 0. So this is one way of writing it. And the other equation will be dava theta dot minus dava L over dava theta. Because your coordinates are now R and theta, right? Two coordinates, and you will have two Lagrange equations. So the answer here will be M R double dot equals 0 if you solve this equation. And this one, you will have MR squared. This is dava L over dava theta dot, yes, MR squared theta double dot equals 0 or something like that. So I just need to mention here that you can do it in both ways, right? So this is the example that we discussed last time. And let me just go for a new two examples. So I'm going to solve two examples today in the class. And from the knowledge that you can get from those two examples, you can try the tutorial and complete it. Right, so the first one will be, so these are two very simple examples. The first one will be about the Atwood machine. Anybody know what is an Atwood machine? This is something that you know, right? Let me draw the diagram so that you will understand what I mean here. So Atwood machine is that you have, yes, so Atwood machine is something that have several pulleys. So you will get the simplest case. So you will have two masses, let's say M1 and M2, connected by a string, and that goes through a pulley. And this is the system that we have. And all of you know that you can solve this problem easily using Newtonian mechanics, just having F equal M, right? So you have done this in your A levels. Now this is the, let me write few details here. One thing that there are two masses M1 and M2 attached to each other by one string that goes to this pulley. So I'm not going to write the question here, but we'll solve the problem. Now one thing that I would like to mention here is total length of the string. Total length of the string is equal to L. Now there are two masses. Anybody have any idea like how many degrees of freedom that I have in this system? There are two masses. Each mass is constrained to move on this vertical plane. So how many degrees of freedom that you have in this system? So just think about that. I will give you some time because once you understand these examples, then it may be easy for you to continue because today will be the last day that we will specifically talk about examples relating to the Lagrange equations until we discuss the tutorial. So you have a pulley. Right, so Sajini tells you just one decrease of freedom. How about the answers from others? Sajid, can you explain why it is just 1 degrees of freedom? You can just unmute your mic and talk. Or anybody else who would like to explain to me why there is only 1 degrees of freedom? Because I am thinking that there are two masses, they should have 2 degrees of freedom.
So is it because it is constrained with the length of the string?
Yes, exactly. Thank you. So that is actually the reason. The M1 under in general, when you have two masses, if each mass can move freely on the space, each of these masses actually have 3 degrees of freedom, right? So M1 will have 3 degrees of freedom x to x, y, and z directions. And M2 also should have 3 degrees of freedom to the x, y, z direction. So altogether, if there are two masses, you will have 6 degrees of freedom if they are free to move anywhere, right? Now, there are two constraints here. Constraint number one is both M1 and M2 are in, if this is a problem, I should tell that both M1 and M2 are free to move only on towards the y direction, which means it can go up or down. M1 can go up and down, and M2 can go up and down, right? So which means both M1 and M2 are now constrained to move along one direction only. So that is y direction, as Naveen pointed out. So which means M1 should have 1 degree of freedom and M2 should have 1 degree of freedom for that constraint. That constraint means it only can move towards y direction or positive y or negative y direction, right? So which means M1 will have 1 degree of freedom and M2 will have another degree of freedom. Altogether, it will be 2 degrees of freedom. However, if you consider the next constraint, which means both M1 and M2 are connected by a string, as Sajini pointed out, right? Because of that, when you fix one mass, let's say you fix M1, then M2 cannot move, right? Because M2 is attached to M1. So let's say if you assume that M1 is uh, right in this position, or you drag M1 to somewhere here, if M1 is here, then M2 has to be somewhere here, because when you take M1 down by a certain distance, then M2 has to go up and should be here. So what this means is when you fix one mass, the other mass is automatically fixed, right? There is no freedom for that mass. So which means because of this second constraint means the length of the string, uh, you will have only 1 degree of freedom here for the system. So this is how you understand how many degrees of freedom that you have in a particular system, right? Because the only thing that you have to figure out is just to figure out how many coordinates that you have to fix the system. Now for in here, if you keep this M1 mass right here, then you need to fix one coordinate, right? That is whatever the y coordinate right here. But once you fix it, then the whole system is fixed. M2 is also fixed from that, which means you only need that particular coordinate to explain the motion of this system, right? So that's how you understand the number of degrees of freedom. Now, if you go back to the previous problem, that there is a particle that you can move on a surface, which means if you need to fix this mass at a particular point, you need to fix both x and y. Right? If you only fix x, then it can move on y direction. If you only fix y, then it can move on to the x direction. And because of that, you will have 2 degrees of freedom in that particular uh, question, right? So this is how you understand how many degrees of freedom that you would have in a system after applying the constraints into the system, right? So that's the way of understanding the number of degrees of freedom, because in for these the large for the for these systems, when you are using the Lagrange equations, it is not like Newton's law. It is very easy because there are only few things that you have to think at the beginning. Number one is you have to identify the system and draw a correct diagram. And number two, you have to identify the number of degrees of freedom after applying you have to identify actually the constraints of the system. Once you understand the constraints, you can decide the number of degrees of freedom. And then the next step will be just write the kinetic energy and the potential energy of the system. And then basically you are done with the problem, right? So it is that much easy in Lagrange equations. Now, if you look at the Newton's equations, then Newton's law itself seems to be simple, but you have to consider all the forces and everything before you apply Newton's law in the system, right? Now, this is why Lagrange equation is very interesting, and that why we are learning it when we are looking at complex systems. So it is more easier to work with Lagrange equations, right? So let's look at how we can solve this simple problem. Now, let me take the height from here to here is x, which means since the total length of the string is L, this height, I can take the other side height is L minus x up to here. Now, I need to find, as I told you, two things. That is, so I know that the number of degrees of freedom is 1. So the degree of freedom here, the only variable will be x in this particular situation. And then I have to, so this will be under gravity, by the way. So I have identified the constraints and the number of degrees of freedom in the system, right? So the next step will be to write the kinetic energy of the system and the potential energy of the system. Right? Can anybody tell me what will be the kinetic energy of this system? Will it be? So everybody knows how to unmute your mic, right? So anyone who would like to volunteer and tell the kinetic energy of the system? At least one of these masses. So there are two masses. One will have kinetic energy and the other one, of course, will have a kinetic energy as well. Wouldn't Naveed? Yes. Okay, Naveen, thank you. I guess it's not completely clear what you are telling, but I will tell what you have mentioned. The kinetic energy of the particle m1 will be half m1 x dot squared, and the kinetic energy of the mass m2 will be again half m2 x dot squared dash L, because both of them should have the same kinetic energy, right? Because if one goes down with the velocity of x dot, the other one should go up. Now the nice thing about using energies is you don't need to worry about the directions, right? Because these are scalar quantities, so that you can just directly write the energy. So this is kinetic energy. Now the total kinetic energy of the system is m1 plus m2 and then x dot squared. So that is T. And then the next step is to write the potential energy. So the potential energy of M1, so let me take the zero level of the potential energy somewhere here. Right? If that is the case, you can see that the potential energy is M1 Gx for the mass M1. Right? So that is minus because I took the potential energy zero level right here. So I measure everything to the downward direction. So that will be minus M1 Gx for the M1 mass. Now there is another mass M2. So that has a potential energy as well. That will be M2G and the distance is L minus X. Or distance or the height is L minus X. Right. So you have two quantities now, the kinetic energy and the potential energy. Now you can write the Lagrangian, that will be L equal kinetic energy minus potential energy. So the kinetic energy is half m1 plus m2 x dot squared minus the potential energy is minus m1 gx minus m2g L minus x. Right. Now just have simplify this. So this will be plus m1 gx plus m2 g times L minus x. Now once you write the Lagrangian, you are almost done with the problem in you use the Lagrange equations because there is nothing to think after that. So you just need to just crank on with the mathematics, right? Apply the Lagrange equation and then solve it and get the equation of motion. So that will be the next step. Right, so let's look at what you would get here. So the Lagrange equation for this one is d over dt. Now it will be the generalized coordinate is x dot, sorry, x. So the Lagrange equation will be something like this. So I just replace q with x because that is the only available generalized coordinate in this particular system. Now let's see the answer for this one. So I'm going to directly solve this because I don't want to like teach you mathematics, right? I guess you have been solving or do the differentiations now for a long time. So so let's first look at what is da by L over da by x dot. So you don't have any x dot terms in these two expressions. So it only comes from the kinetic energy. So that will be m1 plus m2 times x dot. Now, if you take the time derivative of this particular expression, that will be m1 plus m2 times x double dot. So that is the first part of the equation, and then you have to find da by L over da by x. So that comes from the second part, which is the potential energy part, because the first part that contains the kinetic energy does not have any external. So da by L over da by x is m1g minus m2g. So I'm just doing the calculation myself. So just keep an eye on what I am doing and make sure that that you let me know if I am doing anything wrong here, right, in the calculation. So this could be m1 minus m2 times g. Now you get the Lagrange equation. Now this first term right here, so you just need to combine these two terms. That is m1 plus m2 times x double dot and then minus m1 minus m2 times g equals 0. This will give me x double dot equal m1 minus m2 times g divided by m1 plus m2, right? So this will be the acceleration of the system, which is what you would get easily even using the Newton's law. So you just need to apply the F equal ma for two masses, right? And then you can see the difference now. When you apply Newton's law, you basically get the forces involved into the system, and then you have to write these two equations and then add up the two equations so that the tension of the string will cancel out and you will get the answer as uh, the final answer will be the acceleration. So that's how you do it, and you can see that you basically get the same answer again from this particular method as well, right? So this is an easy example, but I just need to show you how you apply uh, the Lagrange equation using one of these simple examples. Now let's look at a little bit different one. So that will be example 2. Now for this one, I am going to give you some time to think about that and then come up with a way of solving it. So there is a, so here is the system. Now for these systems, I am going to draw the diagram for you, and I will, so I want to start you the problem from there. So there is a rod. Let's say this is a rod like this. And then there is a mass. So let me name this mass as M1. And this mass can move along this rod. So it can move along this way or that way. So it is basically constrained to move along this rod. Right? And there is a string attached to this mass M1. And from that string, you will have another mass right here hanged on, so which is M2. And the length of this string is a constant, which is L. So this is the system. Once again, this mass right here can move along this rod in x direction. And while it is moving, there is another mass attached to this mass M1. This is M1 by a string of length L. And the mass of that particular object is M2 and this is the system, right? So then once again M1 can move. So let me just briefly write this here. M1 is constrained to move on a rod, right? And then the other part is like a simple pendulum that you used to have, right? Uh, M2 is attached to M1 using a string of length L. So this is the system, and I want you to write or find the equation of motion or equation of motions of this system, right? Now, few things now you have to first figure out. Number one, uh, let's say number one and two, right? You have to figure out what are the constraints of the system. And the next thing is how many degrees of freedom that you would have for this system. So you have to figure out these two things and then write the kinetic energy and the potential energy and then find the Lagrange equation. Right? Now, uh, so the time is 7:45 now. Rather than I am solving this continuously, I am going to give you some time, probably 5 or 10 minutes, for you to think about this problem. Right? Think about what are the constraints and how many degrees of freedom, and then write the kinetic energy of the system and the potential energy of the system. Right? And if you have an answer, just try to write down it in the chat. Uh, I mean, it may be sometimes harder to write these angles and everything in the chat, but if, try your best to write down an expression for the kinetic energy of the system and then for the potential energy of the system. So it's okay, there will be some mistakes when you are writing it, but I can at least get an idea whether you are heading into the right way, right? So just take 1 or 5 or 10 minutes. And if you have a, so I asked you to have a pen and a paper with you today, right? So make sure that you work out your kinetic energy and the potential energy. And if possible, just write it, write down here for the, in the chat window. So this, you need some time for this one. So I will give you probably 5 or 10 minutes to look at the problem and understand the constraints and all these things and write the kinetic energy and the potential energy, right? Right. So just have a try. So I will, so we will check after 5 or 10 minutes with your answers. So you write any of the ideas that you have about the problem. So try to do this yourself. Now let's look at this system to identify. Now, as a practice, a good way of thinking once again about the degrees of freedom is that you can see that there are two masses as we talked previously. both masses, if they are free to move, each of them will have 3 degrees of freedom, right? So altogether there will be 6 degrees of freedom if they are free to move as they like, right? But now in this particular situation, mass M1 is constrained to move on this rod, on the line, right? So which means that M1 only have like 1 degree of freedom. So it can move on this rod, which means it only have 1 degree of freedom. So let's say it is X, right? So it can move in this direction. So the length that it measures from, let's say, from here to here will be X. So it can move on the road, which means it can change the value of X. So that is then fixed, right? Now, how about the M2? M2 is attached to M1 by a length of L. So which means that length is fixed as well. So now this can move in as a simple pendulum, but however, now this length, since the length is fixed, the only thing that can be changed is this angle, right? I think most of you have correctly identified that, which is a good thing. So so once this is moving, it will change this angle, right? So that is the degree of freedom, or the variable that will change when this thing is moving, right? So I guess all of you who answered has identified the degrees of freedom as 2, uh, which is actually correct. Now, so there are basically 2 degrees of freedom, and so that's the first number one thing. So you have to understand the 2 degrees of freedom. Now you know that you will have 2 Lagrange equations at the end because you have 2 degrees of freedom. Now let's look at how to write the kinetic energy and the potential energy of the system based on this information. Now, there are actually 2 ways of doing this. One way is write everything, and this is actually the more like general way of doing this that everyone can directly understand. One way is just to write everything in Cartesian coordinates and then convert it into generalized coordinates, right? Now, if you remember the proof that we had, remember that we did the same thing. We write everything in terms of r's, and then r can be written as a function of generalized coordinates and then convert everything to generalized coordinates. So we can uh, do the same here, which means consider the 2 objects separately and then write the kinetic energy in terms of Cartesian coordinates and then convert those into generalized coordinates. Right? So let's look at that first, and then I will show you another way of doing it, which is a bit easier. So for the kinetic energy, so there are actually 2 degrees of freedom. Now, this mass M1 has only one coordinate, which is X. Now let me fix the mass M2 by 2 Cartesian coordinates X2 and Y2. Since this is moving on the plane, you can fix this by X2 and Y2. So then you can write the kinetic energy of mass M1 and M2 to the system is half M1 x dot squared plus half M2. Now since you get the 2 coordinates as x2 and y2, you can write x2 dot squared plus y2 dot squared. Right? So this is how normally one would write the the kinetic energy. Right now, you can convert everything using the relations, that is, you can write y2 in terms of L and phi, so that will be minus, or in terms of the length, y2 will be L cosine of phi, right? I guess you can understand it. This is L, then this length will be L cosine of phi. So that will be y2, the value for the y2. And then for the x2 is right here. So that should be the length from, if we measure everything from here, x2 should be equal to this whole length. So that means from here to here you have x, and then plus this length. This length is L cosine of phi, and up to here. So the y2 is L cosine of phi, and then the x2 equal to x plus L sine of phi. Now you know the value of x2 and the value of y2. Now you can write x2 dot and y2 dot, right? So y2 dot means you have to differentiate this expression with respect to time. So L is a constant. Now first, cos phi, you know that it is the one that is changing, which is 1 degree of freedom. So it will change with the time. So when you take the time derivative, that should be the derivative of cos phi is minus sine phi. And then you have to take the time derivative of phi, right, which is phi dot. Uh, Please let me know if any of you cannot understand this, right? So I am under the assumption that you are very familiar with these differentiations. So I am just using the chain rule. So I get differentiate with respect to uh, phi, and then respect to t. So that's how you do it. And then for this one, x2 dot will be equal to uh, so x can move on the line as well, so which means x dot and then plus x dot, you can directly differentiate with respect to time, that will be x dot. And then for the L sine phi, when you differentiate sine phi, that will be cosine of phi, and then again phi dot, right? So you have x2 dot and y2 dot now written in terms of x and phi's, which are the degrees of 2 degrees of freedom that we have identified. Now you can plug these two values in this kinetic energy equation, so that we will convert the equation for the kinetic energy for our generalized coordinates that we have identified. Now, one question that some of you had was, even though you tell that there are 2 degrees of freedom, you are not sure whether there are 2 degrees of freedom or 1 degrees of freedom. Now, uh, the easier way, I mean, if you cannot understand it directly, the easier way to look at initially is look at the two masses like separately. And in general, you should have 6 degrees of freedom, which means for M1, you should have 3 degrees of freedom, and M2, you should have 3 degrees of freedom. And then think about the constraints that you have for M1. So that should be move on this rod, which means you remove two coordinates. You only have 1 degree of freedom to move that only towards X direction. And then go for the M2. And for the M2, the first thing is it only moves on a plane, right? Which means it should only have 2 degrees of freedom. You can eliminate z or y, whatever you think that in that direction. And then out of those two coordinates, then you can see that it is constrained by this length L, right? Which means it cannot move as it wants that towards that direction as well. And then you can see that when you look at the problem, this phi, the angle is changing. So that is the only way that it can change. Now, if I uh, remove this restriction of length L, now this happens when think about the situation that if you have a string that can stretch, right, or a spring, right, and this mass is attached to the spring. So then what happens is, uh, while this is moving in this simple pendulum motion, the mass also can move towards along the line of this length L, because it can stretch and squeeze, right? If it is a spring that can stretch and squeeze, so that you have to consider that direction as well. So which will add up another degree of freedom, right? So that's how, which means the length L will also can change, right? So then you have another extra degree of freedom to the problem. Now, since the length L is fixed here, you don't have to worry about like that. So those are the things that you have to identify, right? I mean, that's a good question, that identifying the number of degrees of freedom and writing the Lagrangian is what is important in all these problems related to Lagrange equations, right? So let me now write the kinetic energy here. Now I know the value of x dot, x2 dot and y2 dot. Now this will be half m1 x dot squared plus half m2. Now x2 dot means x dot plus L phi dot cosine of phi squared plus y dot y2 dot squared means, so I am basically writing this equation right here, that is minus L phi dot sine phi squared right here. Now you have half m1 x dot squared plus half m2. Now you can solve this, what is inside, x dot squared plus L squared phi dot squared was squared phi plus 2x dot L phi dot cosine of phi. So I just have expanded this term right here, and then the other term is L squared phi dot squared sine squared phi. Right now you can see that there are two terms for x dot squared. You can combine those two, m1 plus m2 x dot squared plus uh, you can see that for the next term m2, and if you think about this term and this term, you can combine those two by taking L squared phi dot squared outside, and then you have cosine squared phi plus sine squared phi, which is equal to 1, right? And the last term, which is plus 2x dot L phi dot cosine of phi. So that will be 1. So that we will have half m2 L squared phi dot plus 2x dot L phi dot cosine of phi. So this should be the uh, so there should be brackets inside this. A squared phi dot square 2L x dot phi. Is it phi dot? Yes, this should be phi dot and cosine of phi. So this should be the final expression for the kinetic energy of your system. You can see that you need to have good practice in mathematics, right? Because you have to do a lot of differentiations and solving differential equations, so and so. So make sure that you practice these. So that is why it is very important that you do this yourself, other than me doing it and looking at that. Right? Because you have to do that yourself to practice this. There is no other way of getting around that. Because even in exams, once you write the Lagrange equation, just mathematics that you have to solve yourself. So you have to do it in the correct way and get the final equation of motion. You have to have a good practice of doing this yourself. That is especially by solving problems. So nothing will help this other than you are doing it yourself and doing these calculations, right? Now, sometimes students think that it is not, once you take the Lagrange equation, then you are done, then you don't need to worry about the rest of the things, that you can do it when it comes. But if you are not used to these calculations, then you can't do it, right? And let me tell you this as well. Now, it is true that once you write the Lagrangian, then physics is like over. Then you have to solve this using the differentiation and then solve this differential equation. But that part is also important, uh, and you should give the same weight that you are giving to find the Lagrangian as well. Because think about a very practical situation that you have to go out and solve a problem, right? Uh, Using Lagrange equation, and then you just stop everything by after finding the Lagrangian and give like leave it to somebody else. But so what would happen is, even though you get all the physics correct and have the correct Lagrangian, and then if you ask someone else, or if you are careless after that solving that problem because you think that it's just a routine thing, but if your final calculation is wrong and if it is applied to a practical situation, then you will have problems, right? So you have to be very precise in that section as well. And because of that, especially in Lagrange equations and in classical mechanics, calculations are very important. Right? Make sure that you keep that in mind. While you don't have to think much, you just do the mathematics. You have to do it correct, right? So this is Lagrange kinetic energy. Now let's look at the potential energy. Potential energy is actually easy. So as I guess Inomi has done, it should be minus m2 gl and the cosine of angle, because so if you think that this is the potential energy 0 level, you don't need to worry about m1. It does not have any potential energy. It will be 0. But respect to that level, this m2 mass will have a potential energy of m2 gl cos phi, right? So I think all of you can understand that. So I will write it directly here. Minus m2 gl of cosine of phi. Now you can see that it took some time for me to figure out and do this calculation and find the kinetic energy and the potential energy, right? Now, uh, there is an exception for that. I mean, there is an alternative way of finding this kinetic energy. So let me just show this in different color. So if you look at this system, I don't know whether any of you have figured out this thing, this way of doing it, which is also correct. So you have this mass here, which could move along this line, and then there is this the second mass. So let me take this angle as phi as usual, and this length is x, and this is L. Now, if you are smart enough to figure this out, then the mathematics will be much easier, right? To have this, you can actually write this kinetic energy directly if you figure this out. Now, this is what I was actually mentioning last week as well. If you look at the geometry of the problem and you have a good idea how the system behaves, you can use this method. Now, if you think about the kinetic energy, of course, this has a kinetic energy x dot, that is mass m1, and then there is mass m2 right here. And if you think about how this mass moves and what are the velocity vectors that applies on this, there are actually two vectors. One is that when it moves, it has a velocity towards this direction, and this velocity is actually what? L times phi dot. So you know V equal R theta equation, right? So this is by actually writing directly the velocity in terms of polar coordinates. The L is fixed, so you don't need to worry about that. And then the angle phi is what is changing. Now the velocity applied on this mass is L phi dot. Now the question is this the only velocity that applies on this particular mass? So there is another velocity that applies, right? So because the mass moves in this way, you can think that this is one velocity that applies on this mass. And because the second mass m2 also moves with this system mass m1, this mass also have the same velocity that m1 has, right? And because of that, there is another velocity towards this direction, that is x dot. Because you can see that the whole system moves when m1 moves along the road with the velocity of x dot. Since this m2 is attached to m1, m2 also has the same velocity towards the same direction, right? So that's how the system moves. Now, if you directly figure this out, the things will be much easier. Now, this angle will be, if you extend this and this angle will be 90 minus 5. So this is 90 minus 5. So this angle will be 5. Now, if you need to write the total energy of the system, you can directly write it. Total energy of the system will be equal to energy of the mass m1, total kinetic energy, m1 x dot squared. So that is the kinetic energy of the mass m1. How about the mass m2? Half m2, and then you have to figure out the velocity uh, of the mass m2. Now you have two velocities, right? X dot t is towards this direction, and then the L phi dot t is towards that direction, right? When you have, you know that velocity is a vector. When you have two vectors that act with an angle of phi, you know this equation that you uh, have probably learned in your A levels. When you have two vectors angled into like angle of phi, then you can write this the resultant vector. When you have p and q two vectors, p squared plus q squared plus 2pq and the cosine of angle between those two vectors, right? So that's how you normally write it. And you can use the same thing here, because you have to write the square of the velocity. That will be one vector x dot squared, and the other vector is L phi dot squared. So that means L squared phi dot squared plus 2 times the multiplication of the two vectors. So that is x dot L phi dot and the cosine of the angle, cosine of phi. And see that you can directly get the same equation right here. Right? See how easy it is if you figured out how the system behaves. Right? So this will reduce a lot of mathematics. But you have to be careful. Now there are two methods. It does not matter which method that you like use, but it is always very it will reduce a lot of work when you do it in this way. You identify how the system behaves and what is the geometry of the system, how this mass is moving on the plane, then it will be much easier to figure out the kinetic energy and the potential energy, right? Now, in most of the lectures, you would see that even in these online lectures that I have posted, they first write everything in terms of Cartesian coordinates and then convert it into generalized coordinates, which is perfectly fine and okay to do, and also safer to do it in that way. But if I were you, I would use this method when if you are very confident, this will be a very easy way of doing it, right? You just look at the problem and look at the geometry, how things are moving. I mean, you just need to get the physical sense or the idea how the system behaves. Then it will be much easier. And in the tutorial, there are problems like this. So depending on which way that you choose to do it, your mathematics will be much easier, right? Right now you have the kinetic energy, and let me write the potential energy will be the same. It will not change, minus mgl cosine of phi. Now, if you do it in this way, you directly write these two rather than writing all these steps, right? So that's what I want to show here. Now there are two coordinates, which means you will have two differential equations. Let me first write the one with the x. So that will be da by L over da by x dot minus da by L over da by x equal to 0. Okay, let me just write the expression for the Lagrangian, which maybe it will be more clear that way. So L is equal to T minus V, T equal half M1 x dot squared plus half M2 x dot squared plus L squared dot phi squared plus 2x dot L phi dot cosine of phi, and then minus minus, it will become plus, and mgl cosine of phi. Now let me write. I mean, after that it's straightforward, you can do it. But for the first two examples, I will do the mathematics part as well. So let's look at what is da by L over da by x dot. From L, here you will get M1 x dot plus only term that comes from here is, now it should be M2 x dot plus M2 L phi dot cosine of phi. So that's da by L over da by x dot. Anyone tell me the answer for the da by L over da by x? What is this answer? The da by L over da by x. Now, if you look at the Lagrangian right here, now these are some of the things which will be related to conserved quantities that we will talk probably the next day, right? So just look at the Lagrangian. Yes, the answer is Taranga says it's 0. It should be 0 because you don't have any x variables in the Lagrangian, which means when you take the derivative of x, this answer for this one will be 0, right? So that you will have only the first term of the Lagrangian. Now you need to take the time derivative of this one, da by L over da by x dot. So that will be m1 plus m2 x double dot plus. Now this one you have to be careful when you take the time derivative because m2l is constant, but there are two terms here, phi dot and cosine phi. Both should be differentiated with respect to time, right? Which means you have to use and the multiplication law in differentiation for this one, which means first you differentiate phi dot, which will be phi double dot and cosine of phi, and then plus you keep phi dot and differentiate cosine phi, which will give you sine of phi. So this will be the final answer. Is it correct? Phi dot. No, actually sine of phi, then you have to have another phi dot, right? Because when you differentiate sine phi with respect to time, cosine phi with respect to time, it will be minus sine phi. Then you have to differentiate phi as a, which will give you phi dot. So these are the places actually you have to be very careful when you do this differentiation, right? Because missing of one of these terms will affect the final answer, because the idea is that when you take the equation of motion, you are going to predict how this particle behaves, right, on the space. Now, if your final answer is wrong, you will predict completely wrong behavior. Right? This is why the mathematics part is important here. So let me write this again. M2L phi dot cosine of phi minus phi dot squared sine phi equals 0. So this is what you would have as one equation of motion. You can see that the equation of motion, this equation of motion itself is coupled with phi and x dots, which is actually not a simple one to solve. Right, so now let's go and look at the other equation, which is da by L over da by phi dot. Now you have to look at this Lagrangian and see how you can get an expression for phi dot. So the first term does not contribute. It's only the half m2. This is m1, m2. Sorry, this should be m2, not m2, and the phi dot comes from one of these L squared phi dot, and the other one is one phi dot is here and the other one is right here, so it should be 2 cancels out, m2 x dot L cosine of phi, m2 L cosine of phi. Yes, so the phi dot cancels out. Yes. So make sure just double check my calculations. If anything is wrong, uh, just let me know when you do it. Just do it yourself, these calculations. And if you see anything is wrong, then let me know. So this is M2L cosine of phi into L squared phi dot and L cosine phi, and there is x dot, right? X dot is here. Yeah, so this is what I get for the da by law, da by phi dot, but just double check with the whether I'm doing it correct or not. So then you take the time derivative of this one, and then that will be again. Oh, for the phi dot, you don't have half here, right? You don't need to have the half here. That cancels out with phi dot squared. That 2 comes in front. So it will be m2 L squared phi dot and 2 Lx Lx dot cosine of phi. Yes. Yes. Now this is the expression. Now then you take the time derivative. So that will give you m2 L squared phi double dot plus m2. Once again you have two terms here, x dot and cosine phi, which are both are variables with respect to time. So which means you need to take both variables. That will be x double dot cosine phi, and then you keep x dot, and cosine phi should be phi dot sine phi. Just do this yourself. So I'm directly writing it as these are just calculations, right? X dot phi dot and sine phi. So that will be for the first part, and then I have to find Daba L over Daba phi from the Lagrange. That is the Lagrange right here. So phi term is in this term right here, and this one as well. So let me write this. So it will be m2 x dot L phi dot sine phi, and minus should be here. Just give me a minute for this. Right. Sorry, I guess I have unmuted the mic, right? So probably you have not heard me. Sorry about that. So let me just summarize what I have told. For some reason, the mic was unmuted. Uh, so what I was mentioning is that you write uh, the two Lagrange equations. I get you can understand that. So you write the expression for dabba L over dabba phi dot, and then for the dabba L over dabba phi, then I combine the two expressions to write the final Lagrange equation for that degree of freedom for phi's, right? Now, once you wrote these Lagrange equations, so what I have mentioned here is that it seems that the equation seems to be a bit complicated, so that it is not easy to check whether our answer is correct or not. Right? Now, for this case, you can see that these differential equations are not straightforward to solve, and to check whether our answer seems to make sense, I am going to use one of the limiting cases. Remember that I talked about this on the very first day. If you need to check one of the answers whether it is right or wrong, just look at the limiting case if you can't solve it. So the limiting case here is I am going to fix this mass right here. So once I fix it, then what happens is it will not move along this rod, right? So it will be fixed. When it is fixed, its velocity will be zero. So the x dot will be zero and the x double dot also will be zero. So what I am expecting is if this point is fixed, then this mass is just like a simple pendulum that we used to talk, right? So I am going to fix this in the solution and check whether I can get the equation for the simple pendulum, which is what we know. So let's see what happens there. When you fix, the x dot will be 0 and x double dot also will be 0. Then what will happen is, so if I take this equation right here, you can see that if I fix x dot and x double dot, then this term will be 0. When you fix x, then x dots and x double dots will be 0, and this term which contains x dot also will be 0, right? Then what I would get is we will have this term which is m2 L squared phi double dot, and then you have this term which is equal to minus m2 GL sine phi. So m2 will cancel out and while L will cancel out, and then what you would have is uh, phi double dot equal G over L sine phi. What is this equation now? This is actually the equation for a simple pendulum, but not in the way that you wish to have, right? So you probably would expect that phi double dot over G over L times phi, right? So that is what we used to have. But here what has happened was there is sine phi. Actually, this is the correct equation. But what we used to do is we use the small angle approximation, so that when you have a small, we only consider the the simple pendulum under a very restricted case, which is we only consider very small angles. So when you consider small angles or for small oscillations, then you can write the expression sine theta uh, actually very equal to theta, so that you can plug that here. So the phi double dot will be G over L times phi. Now you know how to solve this, right? This is a familiar differential equation that you can solve. At the same time, now you know that your answer is correct under this limiting case, right? So this is how you normally figure out whether your answer makes sense or not. Now, this doesn't mean that you can't solve that differential equation. You can actually solve this differential equation for large angles as well, but you need something called elliptic functions, which comes into play in mathematics, which is a separate branch that you have to look at, which we call as elliptic functions and elliptic integrals. We will not talk about that in this uh, class. And you can see that even though the simple pendulum is a simple problem, even without small oscillations, you can't solve the problem, right? So you have to have these elliptic functions and elliptic integrals. So hopefully, if you go for a PhD or something like that, you may learn it. Depend on the university that you will be going. But for now, so what I just want to um, express here is how to solve this particular problem completely, so that you will get an idea how to use Lagrange, how to draw the diagram, find the degrees of freedom, and then how to write the kinetic and potential energies, and then the Lagrangian, and then solve the Lagrange equation to find the equation of motion. And at the same time, you should be able to figure out these limiting cases. Right. Right. So I will upload this note, which I have these solved problems plus the lecture also during the weekend. Now, anybody have any questions up here?